Hello, student. Welcome back to this topic of time-dependent perturbation theory. So, so far we have seen the transition from state n to state k, and where we had assumed that both the states are discrete ones. That means the state n as well as the state k were assumed as a discrete ones. But now we assume that now we consider the transitions from a discrete state n to a continuum of state around ek. That means k state. So that means the k state is now not a discrete one, it is a continuum. That means energy varies on either side of this state k, which is ek, and where the density of states is rho of ek. Then the density of the state is represented as a rho, this term rho of ek. Density of states means the number of states available per unit energy range is called as the density of states. The number of states in the energy range ek to ek plus dk is uh, is rho of ek into dek. That means just we are multiplying this density of states to this energy range dek gives the number of states available in this range of energy, and the total probability for transition into this range dek is given by this equation, because already just now we discussed the uh, this probability uh, of transition from state n to state k by taking harmonic perturbation as an example. So here also we have considered, or we assume that the perturbation is an harmonic term. So that is why I have taken the derivation from the last session. This was the derivation from the last session, and now to the same term I am multiplying this density of states in this case. So this is the density of states in this particular case, and now the energy is varying on either side of the state k. So when t is large, the width of the main peak becomes small, as I told in the last session. In the plot of that omega k minus omega n, and the probability at a time t is equal to 0, the main peak was there with the high maximum height, and as the time has increased, the sub other peaks were raised, and their height was considerably small. So that is why when t is large, the width as well as the height of the peaks goes down, and that shows that only limited number of final states, that shows that the probability of finding the system in the state k also ceases, and only a limited number of final states contribute to the above integral. That means at a larger time t. Consequently, we can regard h dash kn and rho of ek as constants over this range. So that is why at a higher time ranges, these two quantities can be considered as a constants. To evaluate the integral, the variable of integration may be changed from ek to x by defining x is equal to omega kn minus omega into t divided by 2. Here I will take this quantity, or I will define this quantity x as omega kn minus omega into the bracket t divided by 2. So this because we know that this omega kn is nothing but ek minus en divided by h cross and minus omega. This even this omega can also be written as in general e divided by h cross. So just this term is expanded into t divided by 2 or dx is equal to t divided by 2 h cross into dek. So means this term used to be expanded actually. There is no need of writing this in this way. You let it be omega kn, or we have to write here this also as e by k, e by h cross. We have to write this also as e by h cross. Then the whatever term is there in the numerator, that is some energy. So that is dek, and divided by whole divided by h cross will be there. So this equation becomes de after differentiation. This becomes dek divided by h cross. Dx is equal to x is the dx is equal to dek divided by h cross, and this term is there, t divided by 2 term is there, that is multiplied. So this becomes dx is equal to t divided by 2 h cross into dk. That means it is differentiated with respect to energy, not the time. That is why t is kept as it is. So here I will write this term. This term can also be written in this way, and as I told just now, or you convert this equation. From this equation you will get dek is equal to 2h cross upon t into dx. This is also possible. So all these things in equation 2 we have to substitute into equation 1. Then what happens? We know that this equation 1 becomes like this. Then the probability term becomes like this. The probability pt is equal to, it is 4 divided by h cross square integral of dx and h dash km mod square into sine square x divided by, because now this whatever is there in the sine term, that is omega kn minus omega divided by h cross divided by 2, that we have substituted as a x. So this simply now the sine term becomes simply sine square x divided by omega kn minus omega whole square is there. So it becomes like this, 4x square divided by t square into rho ek, and this is the value of dek is equal to 2h. Here from this from equation 2, dek is equal to 2h cross upon t into dx. So now you cancel whatever the things get cancelled. One h cross is cancelled with this h cross square, and this 4 is cancelled with this 4, and 1 t with this is cancelled with this t square, and I am writing the remaining terms like this. So the probability is equal to 2t upon h cross into h dash kn square into rho of ek into integral of sin square x divided by x square into dx, because here only x square left, and these two taken outside the integral sign, because this thing is for higher time t. So when the time t is large, we have considered these two as a constants. So the only variable is this term, sin square term. The integral term is the only variable term. So the transition from the state En into a state Ek can be on either side of En, as I told. So the transition from En to Ek is on either side of Ek, not En. It's wrong. On either side of Ek. That means because we have considered the state n as a discrete one, whereas the state k is not a discrete, it is a continuous one continuum, and hence the energy spreads on either side of this state ek to some small extent. Though the integral is over a small range of ek is equal to omega k n minus omega, the limits on x can be extended to plus or minus infinity. So we can extend this integral limits to plus or minus infinity to cover the wide range of the energy values. So as the integral is very small outside the actual range, the integral is denoted uh, as the integrand is very small outside the actual range. So even though you are changing the integral limits to plus or minus infinity, nothing happens because this variation is over a small range of energy, and beyond that small range, this function is zero. Hmm? And the integral is a standard one. This integral is a standard one and is given by minus infinity to plus infinity sine square x divided by x square dx. This is equal to pi. The value of this integral is just pi. And substituting this equation 4 into 3, we get the simple form of probability as probability is equal to probability is equal to 2 pi by h cross t, and because the this pi becomes because of this integral, and 2 pi by h cross t and h dash mod square into rho of a k. Then the number of transitions the number of transitions per unit time is called as the transition probability, and is denoted by omega. So that is why this t goes unity, hmm? Because this becomes p by t. This omega is equal to p by t. That means the transition probability per unit time is p by p of t over t. So omega is equal to p of t over t. So this t comes this side. So we are writing the remaining thing 2 5 h cross is equal into h dash kn square into rho of ek. So and this is the very important or the famous relation rule, and this is called as the Fermi golden rule. So the transition probability, as per, according to this Fermi golden rule, the transition probability is proportional to the square of the matrix element of the amplitude of the harmonic perturbing term between states n and k. So here, this transition probability omega is proportional to the square of the harmonic or matrix element or the harmonic term, or the amplitude of the harmonic term. It is h dash k n mod square is the amplitude of the harmonic perturbing term between the states n and k, and to the density of final states here rho of k, and this transition probability is proportional to the density of the final states k. Why it is final states? Because we have assumed here that we have assumed here that the time is large. So when the time is large, already you have the system has gone through a transition, and hence only the final terms only the final terms contribute to the transition, not the initial terms. So that is why rho of k here gives the density of the final states. The intensities of spectral lines are proportional to these transition probabilities, as they depend on the rate of transfer of energy between the electromagnetic field and the system. So this is about the transition of the system from discrete state to a continuum, and indirectly, or in other words, we have derived here the Fermi golden rule of the transition probabilities. Thanks for watching.